Now that we've looked at confidence intervals for the mean, let's talk about confidence intervals of proportion. Not everything is just an average. As an example, if we want to know the percentage of Americans that drink coffee every morning, that would be a proportion rather than a mean. So we need to have confidence intervals for other things. So we'll start off with a little bit of notation. P stands for our population proportion, the portion of the entire population. And P hat is our sample proportion. It's the proportion of the sample that we happen to look at. We're also going to need Q hat, which is 1 minus P hat. It's essentially everyone else. Going back to my example before, if I want to know the percentage of Americans that drink coffee every morning, Q hat would be the percentage of Americans that don't drink coffee every morning. Here's my formula for the confidence intervals for proportions. We have P hat and then plus or minus Z times the square root of P hat Q hat over N, where N is our sample size. And this Z is going back to the same Z that we talked about with confidence intervals for the mean when we knew our sample standard deviation. Here's a table where the left-hand column gives us the level of confidence we have and the right-hand column gives us the Z. So, just like we did when we originally looked at confidence intervals for means, we have the same values for Z. So let's look at a couple of examples. Let's suppose we do a survey of 200 people and we find that 82 of them drink coffee. We want to find a 95% confidence interval. The first thing we need to find is our margin of error, which is that Z times the square root of P hat Q hat over N. A 95% confidence interval, if I look back at that table that I just had, would be 1.96. Now what about P hat? So as a quick side note, P hat is going to be 82 out of 200, the number of people that actually do drink coffee every morning. And if I work that out, I get 0.41. Q hat is then going to be everyone else, which would be 0.59, divided by my sample size of 200. And when I work this out, I get 0.068. So my actual proportion would be that 0.41, the 82 over 200, minus 0.068 is less than the actual proportion, which is less than 0.41 plus 0.068. So if I work that out, I get the proportion is actually somewhere between 0.342 and 0.478, or somewhere between 34.2% and 47.8%. So let's look at another example. Let's suppose we do a survey and find that 23% of students have student loans, and let's suppose we interviewed 1,400 students. We want to find a 90% confidence interval. I'm going to start with that Z alpha over 2 times the square root of P hat Q hat over N. A 90% confidence interval, if I look back at that table, was 1.645 times the square root of P hat, which is 0.23. In my last example, I had to find that, but in this example, it was given to me. Q hat would then be everyone else, 0.77, over my total of 1,400, which gives me 0.019. So now I have 0.23 minus 0.019 and 0.23 plus 0.019. That gives me 0.211 is less than P is less than 0.249. So I've discovered the actual percentage of people who have student loans is somewhere between 21.1% and 24.9%. Just like when we first talked about confidence intervals for means when we knew the population standard deviation, if we already know the error, I can figure out the required sample size. And it's given by this formula. N equal to P hat Q hat times z over e squared, where e is our error. And whenever we do this, we always need to round up. So let's do an example of using this. Let's suppose we want to estimate with 95% confidence. So we have a 95% confidence interval. We want to estimate the number of people or the proportion of people that own a computer at home. Previous studies have given us that 40% own a computer. And we want a margin of error of 2%. So if I look at using my formula, I would have p hat, which I found to be 0.4. Q hat would then be 0.6 times z. 95% confidence intervals gave z to be 1.96 over my margin of error squared, which gives me 2304.96. So we would need 2,305 in our sample size. In this last example, we actually knew a previous study to get p hat. But what if we don't actually know that? What if we still want a 95% confidence interval and we want a 2% error, but we have no idea what happened on a previous study? So p hat and q hat, we have no idea what they could be. How do we actually find the sample size? Well, we can still find it. So I'm going to leave a blank for p and q currently. 95% confidence interval would mean z is 1.96 and our margin of error is 0.02 squared. So what do we do for p hat and q hat? Essentially, if we have absolutely no idea what they are, we're just going to use 1/2. That's essentially going to make our sample size as big as it possibly can be. If p hat or q hat is anything other than 1.95, we would actually need a slightly smaller sample size. So this can tell us at least approximately 2401 if we work this out. So we would need a sample size of at least 2,401.